Okay. Hi, I'm Alexander Lishinsky from GNL, and we talk about media quality assessment. Unfortunately, Adrian Rowe is not here today, so I will cover for him. So let's start with a quick overview. Let me see if it's really as quick as I wanted. So what are we doing? The gap that we are trying to close is usually the live encoder. This is all about live encoder and quality in live streaming. The encoder knows a lot about the quality that it encodes, that it produces. But most of the time we try to rediscover it later in the chain. We have to decode, we have to use DRM keys to look into the quality, to make decisions based on quality. And as this is difficult, we often make decisions for switching between content on metrics that are not as good as they could be because we are losing that quality information before. So what we are trying to achieve is we want to surface the quality where it already exists in the workflow. We want to use standardized names for the quality dimensions and the values that they're attached. And then we want to carry those metrics downstream so that other systems can report on them in a standardized way or can make decisions on them. And the theory behind that, I hand over to Will again.
You have a mic, yeah. I need a clicker though. Thanks, I'm back. There's so many cool projects to work on in this industry. So just some super quick background on this. We look at videos on the right-hand side, right? We tend to use bitrate as a proxy for visual quality. And there's 3 embedded videos. And if I play them, they're all going to look identical, right, visually. So the perceived quality is consistent, but the bitrate of one is 4 times the bitrate of the other. So the real quality depends on a whole lot of other factors. The codec you're choosing, how far you're sitting, what's the brightness of the screen, what are the capabilities of the display device. It's a complex set of visual quality metrics, and we dumb it down, and we just say, oh, bitrate is the representative for this, and that's often not right. So we have an admittedly complex, or not so clear workflow distribution, right? And if we look at which components in this, going from contribution encoders to cloud to remote to origin to player, actually know about the quality. We have metrics like VMAF and PSNR and SSIM, right, that do measure the more complex perceived visual quality, but they're only known by a few components on the screen. So our project very simply, and we use bitrate everywhere else as a project for it. So our project is basically to take that information known by those encoders and propagate it down the distribution workflow so that every component can know what the VMAF score of the segment is, not only the encoder that made it. And what do you do with this once you've got it, right? So same diagram, now laid out linear. So number 1, I can select between 2 contribution encoder sources. They might have the same bitrate, but one's encoding black or fuzziness and the other isn't, right? I can select the one with the better visual quality. 2, at a packager level, I can enable quality-based switching. So I might have 2 encoders that have taken feeds, right? And again, they have equal bitrate, but different quality scores. At the origin shield, where I'm sorting between 2 cloud origins, I can select the one with the better quality, not the one with the highest bitrate. At a player, ultimately, I can track the quality of what was being played. What we've developed is not a quality switching scheme. We're not doing quality-based ABR, which you could do with the data that was at the packager. You could put it in a manifest. But what we do is report it at the player. So you get a trace or an audit. Did that user actually get 4K? How good was it? And at the analytics provider, we can collect the sum total of the quality, what was actually shown and rendered at the player as a set of VMAF scores. So the project began, Dr. Ushipal at Akamai had a patent. We came to the SVTA and we said, hey, we want to extend this and not just have it within the CDN. We want to make it into a bigger program here. And we're very close to publishing this. I estimate Q1 2026 to get out of here. We use a number of things. One of them is the sibling of CMCD, which is CMSD, Common Media Server Data. So we defined a key, org.svta.mqa, and in it, we pack a number of MQA metrics, media quality assessment metrics. I have some pictures, so we've defined a table of them. You can add your own, right? It's an extensible table. We just defined a table of the most common ones here that people are using. And then it's very simple. Here's my CMSD key, and I say, oh, it's got a VMAF score, and its value is 81. And if I've got 2 GOPs in there, like the 3rd example down, I just report the score twice, one applying to each GOP within my segment. In the orange, we defined a catch-all key, which I think is very important. So say you're a provider and you want some way to choose between two encoders that are in different locations. You can invent your own score. We have a placeholder called MQA-video, and it goes from 0 to 100. Higher number is better. You can define how those numbers are generated, and this is simply a mechanism of tagging data or media segments coming out of this and allowing upstream or downstream systems to select the one with the higher quality. We also defined a message for carriage inside SEI, so the encoder can embed the data and then the packager can extract it later. This can be done at a frame level or it can be done at a GOP level, and the packager, if it's coming in at frame, is going to have to apply an aggregation algorithm in order to generate the combined value. We also do it for dash live ingest, where we're pushing the data. So here we would use CMCD, V1 or V2, take your pick. We use the same key because the structure of the data is very consistent between CMSD and CMCD. And you might say, how do you handle low latency, right? Because in low latency, you're producing the start of the segment and pushing it out before you've finished the segment. So you don't know what its average quality score is yet. So in that case, we apply a temporal offset. It's the TR equals 1 attribute at the bottom. And it basically says, if I send data in segment 34, it's actually the quality of segment 32. So we wait for it to be finished, and then we report it in the next one. So your analytics system can still track the quality received over time. You can't use it for quality-based switching, because it's the segment prior. But again, we're not a quality-based switching scheme. We're a quality information distribution scheme. And with that, I'm going to hand over to Adrian, as represented
exactly.
by Alexander.
Yeah, Adrian. I represent Adrian here. So what we now show is a demo that we did with the Norsk SDK by Adrian Rowe's company Ideas. And so what this looks like is practically the same graph that we saw in Will's representation. On the encode part and on the packager part, you see little queues, and then later on you see large queues, and this is for a quality metric that we measured and introduced into that diagram. So the small queue is quality per frame. Later in the packager, it is converted into quality per segment, which is just what we know from the encoder and from the packager. The problem is that quality is not the same as fidelity. And what we are measuring here is practically fidelity. Because if we have a black frame input or a pixelated input, the quality might be even better if we encode it, because it's easier to encode. So that means we are not measuring the actual quality that comes into the system, we're just measuring fidelity. So we need to ideally capture the quality from before the encoding to forward it downstream. So that means that we can think of a lot of filters that we add to the signal that we capture before the encoding, like the transport stream errors for the ingest, decode errors, and everything else. And then we have a lot of metrics that make things a lot more complicated than before. So what can we do then? We try to avoid the metric explosion in using the MQA audio and MQA video aggregation metrics that scale from 0 to 100. 100 is bigger, bigger is better. And we still transport the detailed information that we get from the system just in case somebody needs it. So there is a easy to understand aggregated value, and then there's optional data that carries the detailed specification that we also measured. So then we can, in this case for the demo that we prepared, we add a time scale. So we ingest time using SEI, so that all the two paths that we represent here have the same time base, and that switching between them, although it's not a switching scheme, we can use it, and in the demo it's being used for that, for reporting. We have the same time base, and we have the different MQA audio and MQA video information per frame, then later per segment, and hand it over to the downstream system. And how the system in the demo works behind the scene, I hope it starts working here. So in the top, the 3 graph is the source stream. It's like the on-prem encoder. It ingests the SEI timecode, and then it sends the on-site publication. So it's like the source SRT stream that we then distribute to 2 encoders, the second row and the third row. And those, I think I have to press play here. Yeah, exactly. So we ingest the time code, we send the SRT signal, and then this is downstreamed to the 2 cloud live encoders that we have below that. And if we start the world in a second here, then the signal will start from the on-prem encoder and the SRT signal, and then we will have the 2 encoders, one by one, being fired up So they are both offline right now. And then we can start them the first one here. And it will generate its own transcode, the cloud transcode. So the result will be the first encoder producing the first encode. So on the right, we see now the image of the encoded signal popping up. And then sometime later, we just start the second one, and it will be showing the same signal, but just from a separate cloud transcoding path. And they are in sync because of the SEI signal that we ingested. And then if we move downstream and take a time like 24 hours and measure if they still are in sync, they are still in sync, and we make sure that the SEI injection makes them perfectly synchronized. And so what we see here is the synchronized phase just 24 hours later. That's the end of the Norsk side. Now I hand over to Brandon, who shows us how it's being used.
Great, thanks very much, and thank you for leaving me so much time. Okay, so I'm at the monitoring. What do we do with all this? We need to be able to monitor it, and we need to be able to use it. So the most important thing is what is the data that we're getting, and we've talked about the headers. I won't go into it, but there's just a quick explosion of the headers. CMSD static. In our product we tidy it up a bit to make it a bit more human readable. So what we then need to think about is the data capture. Where am I going to capture this data from? And for this type of workflow, you need to capture it from multiple places. We're capturing it from the two packages. So you've got the A and the B packager, your primary, secondary. We've also created a media quality aware origin that allows you to do the switching. So it's basically looking at both of those feeds and picking the best one. And then it carries on to the CDN, so we measure it there as well. Okay, so in this demonstration, we've got the two A and B. What we're going to do is we're actually going to inject packet loss, just 2% packet loss, into the A feed, and that will trigger a failover to the secondary. And 2%, so we did 2% because that's kind of similar to a satellite rain fade. Okay, play, yeah, good-o. Okay, so we created this little player dashboard with 3 players on it. On the left-hand side, we've got encoder A and encoder B. We burnt in primary and secondary into the videos, and then obviously on the right-hand side, we've got the CDN version, which is the end user, a couple of seconds later. But what we've also doing is we've just taken out that score, that's little green number on the side, and they're all good and green, which is great. And we'll inject some packet loss in a second, and what you'll see is the MQA video score drop, and you'll see it switch from primary to secondary. Now this is, there's a lot of ways to do it, but pulling from both is the best way to do it. So you can see now we've started to get those scores drop. You'll see some visual impairments on the primary, but of course we now CDN. We've switched to secondary. And of course, there's no visual impairments. So you can see that really obvious, and by the way, that's 2% packet loss. So it's just a minor amount of packet loss, and you've got a significantly impaired video. So that's looking great. So we've actually achieved the goal here, which is to continue to watch a high-quality video. Now, of course, we want to be able to monitor this as well. And take some sort of action when that thing's flashing at me now. Sorry, take action when we see a problem. So we just go to the monitoring bit. It looks like a terrible video to me. Here we go. All right, to the monitoring. Okay, so now we've seen that the A pipeline has had the failure. You can dig into this detail. You can actually, probably you can click on that. You can dig a little bit deeper into the headers, and you'll see it's failed. But what's important is it's this CMCD static header that we're getting the data from. And the most important thing that we're using to switch on is the MQA video score, which has dropped to 40 something. So the other one had about a 70 score. In fact, actually, I think I will just go back a little bit and show you what good looks like. And yeah, again, it's all contained in this CMSD static header, which is the thing that's propagating forward all the way from the encoder all the way to the CDN. Now, you also, that's what we're switching on, but we've also collected the other metrics that you guys were talking about, which is, PSNR, structural symmetry, and in this case, it was actually the errors that caused the problem. PSNR and structural symmetry were great because whatever the encoder gets in, and it encodes what it gets, and it does a really good job of that, though the pixelation is still there. Obviously, looking at this over time is important as well, and here we're just seeing it over the last sort of 10 minutes or so. I can switch off the metrics I'm not particularly interested in, and just focus on the errors and the overall score, and that shows us, why we switched. So that's kind of it. Hopefully you found that interesting. Oh, sorry, I need to give one shout out. This is all thanks to inspiration from Nicholas from a couple of years ago.
Finally, someone says it. Thanks.
There you go. Thank you, Nicholas. Big round of applause for Nicholas. Thank you.
Thank you, guys. And same question, like, is it ready for MOQ ingest onto the packager? Because if we want to push the CMSD, right, we need a control track or something, right?
I think it is. MQA is segment-based, right? And it's using CMSD, but it has different modes. So I think for MOQ, we'd want to extend it, assuming we're pushing something that has group boundaries, and those groups are coincident with GOPs, then we might want to make an extension of MQA that specifically acknowledge mock groups and how we transmit the data. We don't have headers there, so we need to define a track, a media timeline track that we could say at this group and ID offset, here is the associated metadata with it. So the short answer is it's not ready yet, but we can make it ready.
Cool. Other questions? Sure. Come here.
So just to follow up on that, the MQA that we're working on in the SVTA, the 2110 spec, that is really GOP focused for SEI, basically anything that's not CMSD or dash ingest. Are you considering, like, just from a terminology standpoint, like MQA here is separate from SVTA kind of MQA 2110? Which number needs to be changed? I don't know who wants to take. I'm just saying, like, because that document's just about ready for publication, but it's very much what you were just saying.
This is the project we're working on, Sean. So
Yeah,
it's no different to it. We're using MQA, and that's the detail. What Sean's added to it is ERTMP signaling, which was something that wasn't finalized by the time we made this.
Right.
So that's an additional. But if your point is it GOP-based? No, if you look at the SEI, it can be frame-based. So you can have quality for every individual frame if that's what's available. But if downstream components typically don't want quality information at a frame frequency, so something in the distribution workflow has to aggregate it and generate a composite score for that GOP.
Cool, thanks.
Okay.
Okay, next we have David. Oh no, final question. Okay, like 10 second question.
What encoder and solution support this one for the initial stage?
Yeah, at the moment, AWS Media Package v2 supports it, as does the Norsk encoder that we showed here. They're the only two that I know of at the moment. I believe YouTube has some sort of proprietary version, but Sean, you'll have to ask Sean about that.
And packager? So this you mentioned about the encoder, but a packager?
Yeah, media package, but it has to be v2.
Yeah, the initial MQA is done by MediaLive upstream of Media Package. Okay, next, David, Daniel.